So how about if I start with, may I have your attention, please? How about if I start with analyzing free fall using concept of torque. I said that we can do that, and indeed we can do it. According to Newton's second law of motion, which relates torque with angular momentum, rate of change in angular momentum of a particle is equal to net torque exerted on the particle. All right, now let's write down what is angular momentum. And actually this relationship is valid no matter which torque we consider exerted on the particle. What do I mean? Why do I say that there is still ambiguity if I just say torque exerted on the particle? Where is the net torque exerted on the particle? Where is the ambiguity? Where is the reference point? Correct. So this is torque about what? It doesn't matter. Torque about any point is related to angular momentum of the particle about the same point. Be sure, actually, in the future when you solve problems, that you do not change the reference point. You calculate everything about the same reference point. All right. So, according to definition of angular momentum, I can write down that this expression over here is product of position of the particle with respect to that reference point about which we calculate torque multiplied by momentum. I have to take the derivative of this with respect to time. So here I have a product, and actually I recognize that here I have mass times velocity. Momentum is mass times velocity. So I can use now the product rule. So we'll have rate of change of position with respect to time multiplied by product of mass and velocity plus position of the particle multiplied by rate of change in momentum. And I can write down rate of change in momentum that, how about if I just write out d over dt of mass of the particle multiplied by velocity of the particle. Well, yesterday we already saw that rate of change in position is velocity, right? Here I have vector product of velocity with velocity. How much is that? If I multiply velocity by velocity, I will get a zero vector, correct, because they are in the same direction. So this is zero vector, and here I will have position multiplied. Mass for a particle is constant. I can take it in front, and I will have rate of change in velocity. Can you see that? So really over here I have mass times acceleration. Do you see that? All right, let's now see what we have on the other side. Here I have to take net torque, and I'm talking about falling object. So what is the net force? Let's identify all interactions. I mean, for a falling object. There is just gravitational interaction, correct. So really the net torque is equal to the gravitational torque. And gravitational torque, and I have to consider about the same point as I consider that angular momentum. So it means that I have to take position of the particle multiplied by mass of the particle, by its weight. Mass of the particle and acceleration due to gravity. All right, so let's now I have this sequence of expressions, and well, I can recognize that I have here product of position times something. Here is product of position and times something. And on top of it, actually, I can take position about any point. This requires that the second factors have to be equal as well, which means that this factor must be equal to this factor. And I see that I have m over here, and I have m over here. My conclusion is that acceleration of the falling particle is equal to acceleration due to gravity. And we came back to what we actually could conclude much faster from what? The first version of Newton's second law. Because the first version of Newton's second law just said that mass times acceleration of the particle is equal to the net force. Right? Now net force is just gravitational force, is mg. Well, so I conclude that acceleration is equal to acceleration due to gravity. See that it doesn't matter which version of Newton's second law I used, I always got to the expression for, the same expression for the acceleration. Well, now, does it make sense actually to figure out the acceleration of a free falling particle from its angular momentum? Does it? No. Amber says no, and she is right. Why? No, it's not the reason. It's too much work, although what do you mean by work? Who is working? We. Mental work, right? It's too complicated. What I did over here, using Newton's second law for angular momentum, this is the same thing, the same conclusion from the first version of Newton's second law. All right. Now, well, why don't we take a look at a certain application of the relationship between torque and angular momentum for a planet. And let's now consider how we move in space. So let's say that take a look at actually Earth. Well, if Earth is moving in a circle like that, its angular momentum, consistently with the drawing, is up. Can you see that? Yeah, because if I walk forward, show me with your hand what is the direction of my angular momentum. If I walk that way, what is the direction of my angular momentum about you? Up. Correct. It's up. Now, if I go this way, my angular momentum about you is up. Note, by the way, that it depends on this who is looking, because how about if I walk along the aisle? Show me my angular momentum about you. See that? This side of the room says that it's up. This side says that it's down, and it's correct. Both are correct. Angular momentum, because it depends on that relative position. So it could be one way or the other. Well, anyway, Earth's angular momentum is up. How about its momentum? If I walk that way, my angular momentum is up about you. What is the direction of my momentum? That way, consistent with the direction of velocity. Great. All right. Now, look at this picture and figure out gravitational torque exerted on the Earth by considering that Earth is a particle. Gravitational torque exerted on Earth. Talk to each other. What is the direction of the gravitational torque? About a gravitational torque about the center of the sun. So the reference point is at the center of the sun, which means that the position vector of the Earth is represented by this arrow over here. This is the position vector of the Earth. Right? Now, which way is the gravitational force? Toward the sun. All right? So, position is away from the sun. Force is in the opposite direction. Evaluate torque. 0. Why? Sine of 180 degrees. So, if you consider magnitude, not the product, not the vector product, but magnitude of the vector product, it will be magnitude of the first vector, which means that it will be radius of the orbit, times magnitude of the second vector, which means that it will be magnitude of the gravitational force exerted by the sun on the Earth, times sine of 180 degrees, which happens to be 0. So magnitude is going to be 0. There is only one vector which has 0 magnitude, is the 0 vector. Correct. So torque, gravitational torque exerted on Earth is 0. What else is exerting torque on Earth as it runs around the sun? I mean, in this system. Can you find out more forces? None. Correct. That's good. That's it. So gravitational force happens to be equal to the net force. Gravitational torque, therefore, is equal to the net torque. So net torque is how much? 0. The net torque is 0, which means that the rate of change in angular momentum of the Earth is 0, or of the planet is 0. I see what are the consequences. So I will write down that I already concentrated on the magnitude of angular momentum. So I wrote that magnitude of angular momentum is also constant. I can recognize that angular momentum will be always up. So let's concentrate on magnitude. Oh, a component. No, but I want magnitude, really. Well, if magnitude of angular momentum is constant, then if I divide it by 2 times mass of the Earth, it is going to be constant as well. And in a moment you will see why I divided by 2 times mass of the Earth. Well, so I copied this 1 over 2m, and I wrote what is really magnitude of angular momentum. It is position of the Earth, of the center of the Earth, the Earth, because we are considering as a particle, with respect to the sun, multiplied by mass of the of Earth, times its velocity. Now I have to consider it I want to consider it in an inertial reference frame, and for solar system, the reference frame of the stars actually is inertial. So really, I have origin at the center of the sun, and the axes point at particular stars, so that the axes don't turn with respect to the stars. In this reference frame, Earth is moving in an orbit. So in this reference frame, I mean, this is the velocity considered in such a reference frame. Now, let's take a look. Oh, I can take out mass in front, and mass cancels. And I can also write down that velocity is rate of change in position with and take this time outside from the expression for magnitude. Now I want you to take a closer look at this vector product. Well, this is dr. And actually, it's true in geometry. I mean, you could generalize it in geometry as well. Now, how about actually if I do it? If I make a, let's say, vector A, vector B, and I calculate magnitude of vector A times vector B, 1/2 of that. So I'm going to get 1/2 magnitude of the first vector times magnitude of the second vector times sine of the angle between them. So here is that angle. Now, if I multiply, think about what will happen if I multiply magnitude. Now, on this drawing, magnitude is represented by the length, right? So you can think that this is length of this arrow, B is length of this arrow, and then I multiply it by sine of this angle. If I multiply this length by sine of this angle, what am I going to get? I mean, geometrically. Well, I will get this height over here. Do you see that? Which means that this expression is equal to what? Well, I know how you would recognize it. If I wrote that this length is c, right? So here I have 1/2 c. Now b sine alpha is h. What's that? A what? Yeah, 1 times base times height. What does it give me? The area of the triangle, correct. So 1/2 of the magnitude of vector product formed by the sides of triangle gives the area of the triangle. Now you can recognize why I wanted to have this 2 over here, because now I have 1/2 of such a vector product, and I also wanted this mass of the Earth over here so that I can get rid of this mass over here. And now I have just 1/2 of the area of the triangle, of this triangle. So really, this expression here says that it is the rate at which actually that position vector sweeps area along the plane of the orbit. Can you see that? This is known as one of the Kepler's laws. It's second Kepler law. It says that if planet moves along its orbit, the position vector sweeps always the same area in the same period of time. So, for example, if an object moves in a circular orbit, then it always moves at a constant kind of the same angular velocity. Now, if a planet or any stellar object moves along elliptical orbit, sun would have to be at the focus of the planets of the orbits. Actually, this orbit is not really right. I see it now, but close enough. The point is that when the triangle is elongated, it's narrow. When the planet gets closer, it gets wider. It moves faster when it is near the sun, and slower when it is further away from the sun. This is conclusion from Newton's second law for angular momentum. Angular momentum is conserved about the sun. We could actually make the same conclusion based on work energy theorem, because I can recognize that potential energy, gravitational potential energy over here is higher than gravitational potential over there. And there is only conservative interaction, so mechanical energy has to be conserved. Well, if potential energy here is lower, it means that kinetic energy has to be higher. So now again, from all laws, from all versions of Newton's second law and from all versions of work energy theorem, we could come to the same conclusion like we came now from Newton's second law for angular momentum. All right. Now the next version of Newton's second law, it also refers to angular momentum. How about different angular momentum? What angular momentum did we discuss yesterday? Which angular momentum was related to which torque? For a particle. Angular momentum of a particle about a certain reference point was related to the net torque exerted on the particle, about the same point. Now, if I have a system of particles, how about if I consider now total angular momentum? And total angular momentum is defined the same way as any total value of a quantity. How do we do that? What is total? Sum of that quantity for individual particles. So total angular momentum, by definition, is sum of angular momenta of all particles constituting the system. Now, where did I get this from? Instead of having derivative of the sum, I wrote that it's sum of derivatives. It's mathematical property of the derivative, correct. How did I get that one? That one is actually already a physical conclusion. Where did I get this from? From Newton's second law. Which version? The previous one. What was the previous one? Fifth. From the fifth, I think. Yeah. Correct. From the previous version of Newton's second law. Now, what is this torque net I? What do we mean by that? It is torque exerted on the ith particle due to whatever interaction it is exposed to. So, no matter if these are external interactions or internal interactions within the system. Internal interactions in the system have to be included here as well. Well, however, I can separate now external interaction with internal interactions. And because of Newton's third law, I mean, here I have to add over all particles. So torque exerted by particle I on particle j happens to be opposite to the torque exerted by particle j on particle ith. Similarly, like with forces. So these torques, internal torques, are going to cancel out. And so we will have to add only external torques on the particle. So I can write down that this is the net torque exerted on the system. So Newton's second law of motion for the total angular momentum says that in an inertial reference frame, the net external torque exerted on a system of particles is equal to the rate of change in its total angular momentum. If we say angular momentum of a system, it would be like saying mass of a system. How do we understand phrase mass of a system? Sum of masses of all particles constituting the system. So we understand really as the total mass of the system. So you don't always have to say total, but it's good that you keep in mind that it's total. All right, now I'll give you an example over here. Let's say that we have a two-particle system. It's easier always to comprehend things on systems which have small number of particles. So let's think about two-particle system, and well, we have that these two particles are separated by a certain distance, and they rotate, so they interact. They pull each other so they both move in a circular, along circular paths. For simplicity, we will also let's assume also that these are identical particles. Now, let's say that the radius of their path is a, and they interact in such a way that they get closer to each other. Which means that they really change the object is going to change the shape. Well, we change the shape due to internal interactions, mainly. I mean, it's not true really, because external forces really will tell you if you can change or not. If you, for example, go to worlds of fun and have a ride on Omegatron, that normal force required for you to maintain in that circular motion is so strong that actually you are pinned to the wall of that Omegatron and you cannot change the shape. Your internal forces actually are too weak to balance those external forces exerted on the parts of your body. All right. But let's say that this system is isolated, that these two particles don't interact with anything else but with each other, and they change the shape. I mean, the object changes the shape. They get closer. Well, it means that what will happen with the angular momentum, total angular momentum of the system if it does not interact with external objects. It's not only that the external torque is zero, it's zero because it doesn't interact with external sources. So what will be what can you say about angular momentum? Well, according to the previous version, to the last version of Newton's second law, total angular momentum, rate of change in total angular momentum is supposed to be equal to the net external torque. If net external torque is zero, it means that what? That it won't change. The derivative of angular momentum with respect to time is zero. So angular momentum is conserved. All right. So how about if you write down the expression for angular momentum? And we can even recognize that angular momentum in both cases, let's say it's up. So how about if we think just about magnitude of that angular momentum? So angular momentum, total angular momentum of the two particles when in the initial configuration. Now note, and for simplicity, why don't we consider angular momentum about the center of rotation? So it's center of the point about which they orbit. So now, let's say that they rotate that way. So momentum of this particle, of the right-hand side particle, will be which way? Momentum. In, correct. Its angular momentum will be up, correct. Now let's take a look at the other particle, the second particle. What will be the direction of momentum of that particle? This way. How about angular momentum? Aha, some people say up, some people say down. Well, reference point is in the middle, between the two particles. Still up. I mean, really, if I choose another one, it happens that I would make the same conclusion, because, I mean, let's say that I consider a point over here. Angular momentum of this particle will be which way? Up. Angular momentum of this one will be down. About a point over here, angular momentum of this particle would be down. Now, which one would be greater in magnitude if they move with the same velocity? Let's say if they move with the same velocity, magnitudes of momenta are equal. Yeah, that one will be greater. Why? Because position vector is longer. But so no matter actually, but it's coincidence. Because I mean, like, not always, doesn't always happen that under certain circumstances it happens. I mean, I can say when center of mass doesn't move of a system, then angular momentum about every point will have the same value. So because of that, I picked a convenient point, and always choose a convenient point. Okay, we have a certain comment. Can you shout it?
So when you talked about the point to the left, so does it change? Does the momentum change in each particle every like 90 degrees or something? Because
yes, correct. Yes, very good. Momentum. Yeah, and actually. Oh, I like it. Yeah, because fact that angular momentum doesn't change does not mean that individual momenta don't change. Because indeed, I mean, if the particles interact, well, they move like that along a circle. So momentum is changing all the time. However, angular momentum is not, because now think what will happen. What will happen if this particle gets in front? So it is going to travel in this direction, and position vector will be like this, right? So angular momentum still is going to be up. And, well, this is actually the reason we have concept of angular momentum. We don't like quantities which widely change. So over here, rather than thinking about momentum which is constantly varying of a single particle, we can think about quantity which is constant for a particle. Do you see that? Do you understand that? I mean, this is the reason that we have so many versions of Newton's second law and so many versions of work energy theorem. Because depending on the situation, we can recognize, well, these analysis will be simple if we approach it that way. Because, I mean, if you think about what we are doing entire semester, from the beginning of the semester, what did we do? We did nothing. I mean, very little. We all the time, we are relating interaction with motion. Yeah, it is that we look at the surrounding, we figure out how object interacts and predict what it is going to do. This is one thing one purpose of engineering. Another purpose of engineering, we wanted to do something, how to design interactions. And we are doing this for entire semester so far. Through Newton's versions of Newton's second law, versions of work energy theorem. Actually, we had one more law which linked motion with interaction. What was that? Not Newton's second law and not work energy theorem. I tell you when it was convenient. It was convenient in collisions. A what? Yeah, there was, I mean, as a result of this law, we got conservation of momentum, total momentum. Yeah, from what law? Which linked interaction with motion. So indeed, motion was described in terms of momentum. And what was the interaction? Was impulse, correct. And the theorem was, or the law was called impulse momentum theorem, correct. This is different than work energy theorem on Newton's second law. All right. So let's come back to this situation. All right, so magnitude of the total angular momentum when the two particles are separated by this, I mean, they move along a path of radius a, well, is going to be 2 times now magnitude of the position vector, so it will be radius, times product of mass and velocity, mass and speed, because it's magnitude of mass and speed. So this is magnitude of momentum times sine of the angle between the two vectors. What is the angle between the two vectors? Position vector and velocity. 90 degrees. Sine of, yeah, because it's going in. Sine of 90 degrees is 1. So this is angular momentum of single particle. We figured out that the second particle has symmetrical angular momentum, so total angular momentum, magnitude of the total angular momentum is just that expression. Now, I can relate it, although I don't have to, but because the question was about angular velocity, so I will now express the speed over here in terms of magnitude of angular velocity. And I mean, if you come back to the uniform circular motion, you can recall that velocity of a particle is equal to its angular velocity multiplied by position vector. So speed, therefore, this speed is going to be magnitude of angular velocity, which I marked over here, times magnitude of position vector, which is radius. So this is how I got another A, times sine of the angles between the two. So it's sine of angle between this vector and this direction. So it's this 90 degrees. Do you understand that? All right. Well, if we do the same thing for a situation when the objects are closer, I can express it in terms of also in terms of radius of the path of each particle and magnitude of angular velocity in this configuration. Now, the net torque, the net external torque is how much in this case? 0, which means the total angular momentum is conserved, which means that these two expressions must be equal. Well, if these two expressions are equal, 2 and 2 cancels, m and m cancels, and I have a relationship between angular velocity, or magnitude of angular velocity when objects are closer to when they are further away. They get, so for example, if the two objects get closer, does the angular velocity, magnitude of angular velocity increase or decrease? Increases, correct. How about actually if we make an experiment with that? Oops. I brought a platform here. And two particles. Unfortunately, they don't want to interact. I mean, their gravitational interaction or any type of interaction is too small, so I need a force in between. And Taylor is familiar with the platform. Maybe would you like to come again? You say? No, you are doing fine. Now these objects are heavier because the effect will be stronger then. So why don't you get on the platform again?
It's like mini shot puts.
All right, and now let's recreate the situation which we had over there. So let's ask Taylor to align those particles as they were supposed to be on the drawing. Like that, correct. Now I will. All right, now let's do what was supposed to happen now.
What was that?
Pull them in.
Ooh.
Make it faster.
Oh.
And now quickly.
Okay.
Do you want to try again?
All right.
Okay, so I won't make it. Make it now. Do it apart. Move it. Okay, great. Thank you. Thank you. Yeah. So we indeed see that what we predicted over there happens. Now, I want to give you a puzzle at that point, though, because now let's take a look at for which I have already revealed answer sometimes in the past. I'm just checking if you remember that. Let's analyze total kinetic energy of the two particles. So, I calculate the difference in total kinetic energy in this configuration and in this configuration. So, in this configuration, well, I have mass of the particle. This is square of the speed of a single particle divided by 2. So this is kinetic energy of one particle. I multiply by 2 because I have 2 particles. This is identical expression except that I have different magnitudes of angular velocity and different radius. But this is total kinetic energy of the particles at the beginning. Well, I can pull, I can simplify this expression to such an expression. And if it happens that we bring, like Taylor brought the balls closer to each other, so B is less than A, which means that this quotient is going to be greater than 1. So this entire expression is going to be greater than 1. Mass is positive, this square is positive, this square is positive. So it's greater than 0. This expression is greater than 0. Total kinetic energy of the system increased. Who performed the work? Why don't you talk to each other? Make sure to use the right version of work energy theorem. Anybody would like to comment on it? Things. Ian, how about you? You, Ian?
No, Josh.
Oh, Josh. Josh, would you like to say something?
No, thanks.
How about you? Taylor? Who performed the work? Oh, you have an idea. Talk to each other. Who performed the work, and actually what work? What work do we need here? Do we need the work done on the center of mass? Here is one suggestion. We should consider work done on the center of mass. How much work was done on the center of mass? By whom? JD says, right? JD says that work done on the center of mass was 0, which means that kinetic energy should stay. Which kinetic energy should stay constant? Translational. Did it? Yes. How do you, JD, how do you see that translational kinetic energy didn't change? Center of mass didn't move at the beginning, and center of mass did not move afterwards. Even if you look at Josh standing on that platform, his center of mass was not moving, he was just turning around. And when he brought his hands closer, he started to spin faster, but his center of mass was still moving. So actually, at least we figured out that indeed, translational kinetic energy did not change because the net external work done on the center of mass was 0. But here I'm telling you that kinetic energy did change. We say total kinetic energy, correct. Do not confuse total kinetic energy with translational kinetic energy. Translational kinetic energy didn't change, but total kinetic energy did change. So who did the work, and what work? The 2 particles performed work on what? On each other, correct. If you see that, it means that finally you recognize the difference between the last 2 versions of work energy theorem. The one which says, they are both for objects. And finally you got the difference between them. All right, so probably this will be the right point to end the lecture. See you Monday.